You see it happening every single day, a rocket launching into the sky, or even just you taking a walk. It's one of those fundamental rules of the universe, but it's also one of the most confusing. So today, let's unpack Newton's third law of motion.
I mean, just look at this thing, an Atlas V rocket. We're talking hundreds of thousands of kilograms, and it's just defying gravity. It's an awesome display of power for sure, but it kind of brings up a really simple question. Okay, so we all know gravity is pulling this massive thing down, hard. So, what in the world is pushing it up with enough force to get it into space? And you might think, oh, it's pushing off the ground. But look, it's already in the air. So, what's the secret here?
So what is the rocket's big secret? Well, it turns out the answer is actually way simpler and honestly kind of more beautiful than you'd expect.
See, the rocket isn't pushing on the ground. It's not even really pushing on the air around it. What it's actually doing is using its engines to blast superheated gas down. And here's the magic. In response, that same stream of gas pushes the rocket up. It's this mutual push, a total two-way street. And this whole pushback idea, it has a name, and it's what we're really going to dive into. It's called the action-reaction law.
So here's the official wording. For every action force, there's a simultaneous reaction force that is equal in magnitude but opposite in direction. Okay, the two key phrases you really got to lock in on are equal in magnitude and opposite in direction. This means the push of the rocket on that gas is exactly as strong as the push of the gas on the rocket. They're a perfect balanced pair.
And hey, if you want a super simple way to remember this, just think of this phrase. You can't touch without being touched. Literally, anytime you push or pull on something, that something is pushing or pulling right back on you with the exact same force. It's a fundamental rule of how things interact in our universe. No exceptions. But this law isn't just for massive rockets and cool space launches. It's happening literally all around us, all the time. Let's bring it down to earth and talk about how it works with something as simple as your own footsteps. Okay, picture this. You're stepping off a skateboard. To get yourself moving forward, what do? Your foot has to push the skateboard backward. That's your action. And at the exact same moment, the skateboard pushes your foot, and your whole body really, forward. That's the reaction. The result? Bam! You and the board shoot off in opposite directions.
And once you see it, you'll notice this principle is just everywhere. When you're walking, your foot is actually pushing the whole planet Earth backward. And yeah, believe it or not, the Earth is pushing you forward in return. When you swim, you push the water back, the water pushes you forward. Ever let go of a balloon and watched it zip all over the place? Same deal. The balloon pushes air out the back, and that escaping air pushes the balloon forward.
All right, so this all seems pretty straightforward, right? But this is where we hit a wall. There's a question that comes up here that sounds totally logical, but it trips almost everyone up. So let's just tackle it head on.
And this is it. This is the big paradox that gets everybody. If the forces are equal and opposite, why doesn't everything just cancel out? I mean, if I push on a wall with some amount of force and the wall pushes back on me with the exact same force, shouldn't they just cancel each other out? Like, shouldn't it all just be a big stalemate resulting in nothing? It's a really good question. Why does anything move at all?
And right here, this is the aha moment. It's because the forces act on different objects. This is the key. The forces in an action-reaction pair never, ever act on the same object. So they can't cancel each other out because they aren't even playing on the same team, so to speak. Let's break that down just a little more because it's super important. So your push, the action force that acts on the wall, right? But the wall's push, the reaction force that acts on you. One force is on object A, the other is on object B. They're acting on totally separate things, so you can't add them together. It'd be like trying to add the money in your wallet to the money in my wallet and calling it one total. It just doesn't work that way. Okay, so we've established the forces are equal, and they don't cancel out. But does that mean the results of those forces are always equal? Well, the answer might surprise you. Let's imagine two skaters on some super slick ice, almost no friction. One skater pushes off the other. Now, we know from Newton's third law that the force she pushes with is going to be exactly equal to the force he pushes back with. But are they going to move the same way? Let's look at the numbers here. Our first skater has a mass of 50 kilograms. The second one is a little heavier at 70 kilograms. So when she pushes, They both feel an identical force of 70 newtons, just, in opposite directions. So what's going to happen? What's the result? And here we go. Here are the results. The lighter skater, the 50-kilogram one, actually accelerates more, 1.4 meters per second squared. Meanwhile, the heavier skater only accelerates at 1.0 meter per second squared. So wait a minute, the forces were identical, but the results? Totally different. So what gives? Why is that? Well, this is where Newton's third law kind of passes the baton over to his second law. Remember that one? Force equals mass times acceleration. The third law says the forces are the same, but the second law tells us how an object reacts to a force. And it turns out the same exact force has a much bigger effect on a smaller mass. It's that simple. Think about a huge, old-school naval cannon for a second. The explosion inside pushes the cannonball forward with a massive amount of force. That's the action. But at that exact same instant, the cannonball is pushing the cannon backward with the exact same massive force. That's the reaction. We call it recoil. And that kickback, that recoil, is so powerful, that's exactly why they had to tie these giant things down with super thick ropes. Otherwise, they'd go flying off the deck. So there you have it, from a rocket blasting into space, to a cannon firing, to just taking a walk. Every single interaction is a two-way street. The universe just doesn't do one-way forces. So my question to you is, now that you know this, what are you going to see differently when you look at the world around you?